Loading screens ruin immersion. Obviously, I've seen the loading screens here and there in games, right? We all have. However, in my game currently, I don't have loading screens. And if I take a look at Vampire Survivors, there's also no loading screens. Whether that be due to the fact that he didn't want to add them, simply because he didn't think it would add anything to the game, or because the game loads so quickly that he doesn't need any loading screens, right? So what I feel like is, what he's trying to say here, if your game can handle instant transitions, why not, right? It makes the game feel instant. However, a loading screen can also be useful for information and hide loading.
Have you ever been excited to play your favorite game only to have to wait through loading screen after loading screen? I've spent the past 6 years...
I mean, that's Skyrim basically, by the way. That is Skyrim. It's Bethesda Games.
Creating a game engine, and I'll show you how to remove all loading screens from your games. We can do this today because computers are pretty advanced. Years ago, computers could only do one thing at a time, so each feature a game had, like these three, had to be done one after another. And that's why loading screens exist. When you enter a new level, the game has to stop what it's doing and load it. This can take a while, so the game shows you a loading screen while you wait. But computers have multiple threads now, which means they can run different things at the same time.
Yeah, but that doesn't
this
mean...
means you can continue playing on the main...
Yeah, but that doesn't mean that these things can load as fast as you go into the world, bro.
...main thread, while the next level loads on background threads. But it's very likely this will crash your game, because if two threads read the same piece of memory, they might get completely different values. This happens when a thread accesses the same piece of memory over and over again, because that data gets stored in the cache as well. It's much faster to read from the cache than from RAM, so it's a huge optimization boost.
Is it called cache or
cache? If the main thread
cache?
writes a new value to RAM, the other thread will be working with outdated data. And the rules that control when data is copied from RAM to the cache are so obscure that you can't predict it. This is the problem of cache coherency, and there are two ways we can solve it. Let's say we have a list of 5,000 particles that we update on a background thread. Because the background thread is using this particle data often, its location gets stored in its cache. But the main thread might want to spawn more particles, so it allocates a new, larger array. The old memory is free.
Well, why not just keep the memory and write to that directly? That's what I don't understand. If you write to the memory, why not just keep the memory allocated? I don't understand that. Maybe I'm wrong here. Could be wrong. But what if you... Like, you would have to definitely have a lock on this, right? If there's two threads, right? One of them has a lock, then the other one would need to acquire that lock, right? That's basically how threading works. If the background thread acquires a lock, then the other one can probably only read, while this one can write, right? Reading should still be possible. However, you would read like... You could potentially read... data that's not ready. Even if you have, let's say, like, isn't it that he wants to spawn different particles? Expanding array. Let's see what he says.
Something else, but the background thread doesn't know this yet. It'll keep writing particle data to the same memory.
It's a YouTube video, it's not a game, right?
Definitely cause a crash. To fix this, we need to make sure two threads never use the same memory at the same time.
Yeah, it's
we'll
called a lock.
Use the example of a background thread loading a texture. The thread loads the texture from disk and stores it in RAM. Then after it's done, it sets this boolean to true. The main thread then notices this boolean is true and starts sending the texture to the graphics card. But when it's rendered, half of it's missing. This happens because memory isn't guaranteed to sync between the cache and RAM in order. Even though the background thread sets the boolean after loading the texture, the boolean might be sent from the cache to RAM first. The main thread then starts sending the texture to the graphics card before it's ready.
Did that ever happen to you guys? If I call this function, right? Let's take a look at this function in isolation. And then this function returns me this buffer. If it returns me this buffer, I should have the data in memory. So essentially what I'm doing here is I'm supplying an allocated buffer that is zeroed out. It's already allocated. I already have this buffer. Now I'm reading the file into the buffer. After this operation is done, and I'm returning this buffer, I have the data in the memory. So what is he talking here? Is it really the case that writes are written to cache first and not directly to RAM? So basically what he's saying is that from the cache, the changes need to be propagated to the RAM, right?
The main thread then starts sending the texture to the graphics card before it's ready, and that's why it looks corrupted. So this boolean is not a great solution. We need a robust way to know when everything from a thread's cache has been sent to RAM. For this, we'll use a memory fence. This fence lets us know when all previous memory writes have been sent to RAM and every thread can see the data we just wrote.
Okay.
When the texture data is fully written to RAM, the fence will signal true, and the main thread can send the texture to the graphics card.
Okay. I mean, cool.
This sounds like a lot of work, but C# manages fences for us with its task feature. Tasks run.
Maybe that's just because of C#. He's mentioning C# now. Or is this happening in every single programming language? This is a side effect of how CPUs operate. It's language agnostic. You can never directly write to cache, but you don't need to handle the cache flushes in x86 and x64 because it is strong memory model architecture. But you need to handle that in multi-threaded ARM processors, Cakez. So essentially what you're saying is on Windows this wouldn't be a problem, but on, let's say, you can never directly write to RAM, Cakez. So if I have this piece of memory here, right, that is just an array of slots, and I write to that memory, it doesn't mean that it is in RAM, so it could be in cache first and then flush to the RAM, even on the Windows machine, computer. Okay, so what he's saying here with this texture load and true in a thread is true. Like, the reason why I'm questioning this is because this is very interesting. And it is very important to keep that in mind when I will make a 3D game, right? There might be a bunch more textures than I have right now. Right now I just have one, right? A big texture atlas.
The main thread then.
So essentially this is his solution to this.
Not a great solution. We need a robust way to know when everything from a thread's cache has been sent to RAM. For this we'll use a memory fence. This fence lets us know when all previous memory writes have been sent to RAM and every thread can see the data we just wrote. When the texture data is fully written to RAM, the fence will signal true, and the main thread can send the texture to the graphics card. This sounds like a lot of work, but C# manages fences for us with its task feature. Tasks run on background threads and they automatically create a fence when they finish running. The main thread then checks the isCompleted boolean, which returns true when the thread finishes running and its fence is signaled. Let's move away from this code and look at a real demo. I've created this forest scene that has terrain, textures, and models. When the game starts up, none of this is loaded, so we'll show a main menu screen instead. When the player clicks play, we'll use tasks to load each of these from disk. Each frame, the main thread checks these tasks and sends their data to the graphics card when they're done. You can run this demo yourself. Details are in the video description. But the game will stutter whenever it sends data to the graphics card, and this video on screen shows you how to stop that from happening.
Looks very laggy. Anyways, cool. But basically, this doesn't warrant the fact that if you have a lot of stuff to load, it will still take a long time. So a loading screen is still needed. He didn't go into this at all, which I can understand why the loading screens are there. Okay, so that was very insightful, at least from the memory point of view.